Good afternoon, everybody. I'm Dr. Anne Rose Abraham from the Department of Physics, Sacred Heart College, Thelere. First of all, I would like to congratulate and thank the team, Annual Physics Symposium, St. Teresa's College, for giving me an opportunity to present my work in this platform. So today I would like to present the work on development and defect characterization of ferrite nanostructures for tailored applications. Now let us move on to our work. Motivation of the work. Now we all are living in an era of online classes and we all are in requirement of increased data or memory storage devices. The need for development of nanomaterial based IoT sensors are always felt. Nanobots or IoT sensors are used for treatment of COVID-19 patients. We have also seen that nanobots or nanorobots are used to monitor and analyze, detect and analyze the physical activity of COVID-19 patients so that the physical interference with the patients can be avoided as recommended by World Health Organization. So in this scenario we have felt the necessity or requirement of nanomaterials for development of sensors and for expansion of memory devices and memory cards, etc. So let us see a glance of spinel ferrites. What are spinel ferrites? Spinel structures is actually a face-centered cubic structure. The composition with respect to one unit cell is A8, B16 or 32. That is, which can be simplified as AB2O4. So in our case, this becomes MgFe2O4, where magnesium occurs the A sites, iron occurs the B sites, and oxygen in the sites we have. So the spinel structure can either be normal spinel or inverse spinel. So the crystal structure of magnesium ferrite is a partly inverse spinel structure, and hence the chemical formula we have this. So it has the various applications in microwave devices, fabrication, computer memory chips, and high density recording media. So the applications of magnetic materials are related to their magnetic and crystal structure. So we are moving to the structural reconfiguration, magnetic and defect focused studies of calcium substituted magnesium ferrite nanospinel compounds. And this work has been published in the New Journal of Chemistry in the year 2020. And this is the graphical abstract of the work. And the aim of our work is to substitute calcium ions of 5 different concentrations, that is 0%, 20%, 40, 60, 80 and 100% calcium in magnesium ferrite nanocrystals, and investigate its magnetic properties and the structural transformation that occurs in magnesium ferrite nanocrystals on doping with calcium of different concentrations. So what is the methodology we have adopted? The methodology we have adopted is that we have used a salt chill methodology for the synthesis of the samples, and then the concentration and the physical concentration dependent physical properties of the magnesium ferrite nanocrystals were studied using various techniques like X-ray diffraction technique, transmission electron microscopy, optical absorption measurements, then Fourier transform infrared spectroscopy, Mossberg spectroscopy, and finally the defect characterization technique, which is the positron annihilation spectroscopy. Yeah. So now let us see the synthesis of the magnesium calcium ferrite samples. So we have started using aqueous solutions of magnesium nitrate, calcium nitrate and ferric nitrate. These solutions were mixed and sonicated, and PVA, polyvinyl alcohol, was used as the gelating agent. So the resultant solution was stirred dissolved and evaporated at 330 Kelvin until the viscous salt turns into a dark brown gel. And the dried gels were now calcined at 500 degrees Celsius for 5 hours. And the resulting sample was powdered and ground finely to obtain fine powders. And we can see the X-ray diffraction pattern of the magnesium calcium ferrite samples. We can see that the structure transforms from cubic spinel structure to an orthorhombic structure on calcium doping. We can see that from the X-ray diffraction pattern, the fundamental reflections from the planes 220, 311, 400, 511 and 440 characterize the cubic spinel structure of magnesium ferrite. And we can see that for doping of 60% calcium in magnesium ferrite nanocrystal, we can see that some additional peaks like 310, 011 and 121, etc., which corresponds to that of the orthorhombic structure, starts appearing in the XRD pattern. Okay, so after doping with above 60% calcium, we can see that the structure starts transforming to an orthorhombic structure from cubic structure. So this can be observed from this X-ray diffraction pattern. And now The crystallite sizes were analyzed using the Scherer formula. So the decreasing full width at half maximum, which is indicative of the increasing crystallinity and increasing particle sizes of up to 28 nanometer, we were able to detect. And then the Williamson-Hall equation, Hall plot, was used to analyze the strain developed in the samples. So we can see that the strain decreases to vanishing values with increasing calcium concentration, and this is related to the ionic radii of magnesium and the calcium samples. And the lattice parameter and the unit cell volume was calculated. We can see that the lattice parameter DHK, the interplanar spacing DHK is a by root of s square plus k square plus l square, and from that we have calculated the lattice parameter and also the unit cell volume. So we can see that with increase in calcium concentration, the lattice constants A and B increased, while the lattice constant C shows a drastic decrease. And we can see that the unit cell volume also shows a gradual decrease, which is attributed to the oxygen vacancies within the sample. And we can see that the tabulation form, the present table shows the concentration of the calcium, the lattice structure and the lattice constants. We can see that for 0% calcium or the magnesium ferrite sample, we can see that the lattice structure is cubic and the lattice constants values A equal to B equal to C, which corresponds to cubic structure. And when it comes to 0.6, that is 60% calcium, we can see that the structure shows the transformation to orthorhombic until 100% calcium. And we can see that the values A, lattice constants A, B and C are values are different, which is typical for orthorhombic structures. And the UV visual absorption studies shows the band gap, the decrease in band gap with increase in calcium concentration. And then moving to the Fourier transform infrared spectra, the peaks corresponding to the ferrites like iron oxides and oxygen vibrations are found in the FTR spectra of all the samples. Then this is the TEM images. We can see the TEM image of the magnesium ferrite, and then the HRTM image and the SAD pattern of the magnesium ferrite, and D, E and F are the TEM, HRTM and SAD pattern of Mg.4 calcium, 60% calcium, the sample with 60% calcium. And we can see in the last figure, that is GHI are the HRT, TEM, HRTM and SAD patterns of calcium ferrite samples. We can see that the samples are shows a spherical morphology, and the TEM, the lattice planes are calculated from the despacing is calculated from the HRTM, which is also indicative of the crystallinity of the samples. The SAD patterns also shows the crystallinity and also the structure and also the structural transformation. That is, figure C shows indicative of the lattice planes calculated, that is 440, 400311 and 220 planes are corresponding to that of the cubic spinel structure, while the planes that is detected out from the SAD pattern of calcium ferrite shows orthorhombic structure. This is the EDX pattern of the samples. We can see that MgFe2O4, and you can see that calcium starts appearing in the sample when which calcium is stopped, and we can see the EDX spectra of calcium ferrite. And now we can see here the AFM, atomic force microscopy images, and Raman images of magnesium, calcium, ferrite. We can see the Raman, the topography of the samples can be seen from the AFM image, and the Raman image also shows the Raman spectra and the corresponding Raman image or the domain mapping of the developed samples. Here also we can see the AFM image, the three-dimensional topography, and also the Raman image, confocal Raman spectra, and the Raman image of calcium ferrite samples. Now moving to the wonderful and the fascinating positron anucollation lifetime spectroscopy. So positrons, being antiparticles of electrons, give information on electron density within the material. So this is used to determine the atomic and molecular defects within the materials. So while XRD can give measurable information only when defect concentration is high, and TEM is limited by its resolving power. So we can see that positron anucollation spectroscopy has a much higher, which can detect the defects even when the defect concentration is very low. So this is the advantage of using positron anucollation spectroscopy. And we have done this experiments at Saha Institute of Nuclear Physics, Kolkata. So the principle behind this is that when the sample is actually we use a sodium-22 radioactive isotope which acts as a positron source, which is covered in a nickel foil, and it is immersed in a powder sample kept in a glass tube. So the positron enters the sample and the positron gets trapped at the defects, so which undergo annihilation with electrons via emission of 2 gamma rays. So photomultiplier tubes detect the gamma rays and produce, and they measure the gamma rays. So the positrons, when a positron is emitted and gamma ray of energy, a photon of energy 1.276 mega electron volt is emitted, and similar, which acts as a birth signal for the positron. And now when the positron annihilates with electron, a gamma ray of 0.511 mega electron volt is emitted. So the lifetime or the time difference between the emission of 1.27 mega electron volt gamma ray and the annihilation, that is 0.511 mega electron volt gamma ray, acts as the lifetime of the positron. So this lifetime is used to measure the defects in the material of study, because this lifetime is fixed. That means if the material travels a long distance, or if it is having a longer lifetime, it indicates that there are defects. If the electron has got into a defect and have got annihilated there. Okay, so that is how we can understand the defect characterization in materials, or the positron annihilation spectroscopy for the defect characterization in materials. So this is the experimental setup, like I have already discussed, like the positron lifetime spectra is acquired using the computation software Gini, or gamma acquisition and data analysis on the pulse width software. And we use coincidence Doppler broadening spectroscopy measurements for the analyzing the momentum, electron momentum of, and we use a liquid nitrogen. We use the samples are cooled to liquid nitrogen temperature, and the experiment is set up. And we can see a typical positron lifetime spectra in this figure. And this is the positron, the basics of this, and the lifetime spectra we can see in the of our samples of the magnesium calcium ferrite samples. We can see it is plotted from the update from the graph, and we have calculated the mean positron lifetime, which gives a cumulative picture of the defect interaction process taking place in the samples. And we have from the coincidence Doppler broadened spectra, we have calculated the S parameter and the W parameters, which is indicative of the low momentum electrons that get annihilated by the positrons. This is very sensitive to annihilation of positrons within the defects. And we can see the MOSFET parameters, which suggests the ferromagnetic nature of the samples, and also indicates. Now moving to the conclusion. So we have synthesized magnesium calcium ferrite nanocrystals doped with calcium at Mg2 plus sites. So the reducing lattice constants accompany the transformation to the orthorhombic structure. And our final conclusion is that the vacancy type defects, as investigated by positron annihilation spectroscopy, yield information about the structural transformation and the ionic distribution that occurs in ferrite nanosystems. So this paper has been published. This is a paper that was published in the in New Journal of Chemistry in the year 2020. That is defect focused analysis of calcium substitution induced structural transformation of magnesium ferrite nanocrystals. And these are the other papers published in the area in Journal of Physical Chemistry C, and this is in American Institute of Physics, and this is in Physical Chemistry, Chemical Physics. And the next paper in like Philosophical Magazine, and again in AP Conference Producers, and these are book chapters published, and this is the books edited with AP Press, and Taylor and Francis is on optical and molecular physics, and this is the books published on carbon nanotubes. And these are the elsewhere books, which are this is our research group. We can see Professor Nandagoma Kalvikal and Professor Sabu Thomas, my guide, which enabled me to continue, which enabled me to pursue this research work successfully. So now it's time to acknowledge everyone. First of all, my thanks to team Anna Physics Symposium, Kalamis HOD, and all the team behind Ms. Maria and all the team behind Maria Vinay ma'am. And my most acknowledgement to Professor Dr. Nandagoma Kalvikal, the Director and Chair School of Pure Applied Physics, my guide, and Professor Dr. Sabu Thomas, Vice Chancellor of the University, and who's my co-guide, and Professor PMG Nambish and Saha Institute of Nuclear Physics, where I conducted these studies. And my special thanks to Father Prashant, our principal and head of the department, Dr. C.B. Matthew sir, and all faculties, S.H. Devara, Professor Dibankar Das, UGC DAC Center, Kolkata, where I did my magnetic and MOSFET studies, and Dr. Reggie Philip for nonlinear optical studies, and Dr. Samuel Oliver Tobielva from the University of Johannesburg, 2014. Then Professor Azal Lasovic, Institute of Physics, Belgrade, Professor Didier Rauxel, University of Lorraine, France. So thank you all for your patient listening. Thank you so much. Thank you for this wonderful opportunity. Have a great day. Thank you so much.